Hi, I'm Samira. Welcome to session on networking concepts. This session will cover all the concepts of networking, starting from what is a network, how the networks are classified based upon the size of the network, as well as based upon how the nodes are connected to each other. We would then take a look at what are various network impairments or issues in the network and the solution to these. And for the solutions, we are going to focus on both protocols as well as layering. As a part of layer models, we will cover both the TCP IP as well as the OSI model. What is the difference between these two models? What are the layers present in both the models? And we will also take a look at functions of each and every layer of the OSI model. Then we will look at the various network devices, right from switch, hub as well as router. And finally, we will cover what is a collision domain and what is a broadcast domain. So let us begin with the session. Hi, let us start with what is a network. A network is basically a group of computers or devices which are connected together to each other via either a wired media or a wireless media. You can see here in the image we have got devices which are connected, some of them connected via wireless media, some of them connected via a wired media. The purpose of this type of a connection between devices is to share information. That is, if one of my hosts wants to communicate with other hosts on the network, it is going to communicate using this media. Another purpose of having a network is to share resources. For example, a group of devices want to use a common printer. In such cases, you are going to have all of the devices connected on a common network as well as the printer on the same network. That is going to help multiple devices to share the printer. If we have multiple devices which want to communicate with each other, they can communicate either using circuit switched technology or packet switch technology. So what basically do you mean by circuit switching and packet switching? The PSTN or your telephones or the landline phones use circuit switching technology, wherein the devices can communicate with each other only after a circuit is being established between them. So in that case, they are going to go through three phases: a circuit establishment phase, then communication, and lastly the circuit termination phase. Versus that, we have got packet switch technology, in which when a device wants to communicate with other device, it is directly going to have the message sent. This message is going to be divided into smaller parts called packets. Each and every packet is going to be traversed over the network independent of every other packet. Circuit switch technology is costly as compared to packet switched, because in case of circuit switching, you have a dedicated connection between the two devices. Only then they would be able to communicate with each other. Whereas in case of packet switching, multiple devices are going to share the connection with other devices, and hence it is cheaper as compared to circuit switching. Next, we move on to network classification. Networks can be classified based upon the size of the network as LAN, which is local area network. Then we have MAN, metropolitan area network, WAN, wide area network. We also have got smaller networks like PAN, which is personal area network. Based upon how nodes are connected with each other, we can classify the networks as mesh, bus, ring, star, tree or hybrid. These are called as topologies of network. Let us begin with LAN. A LAN connects network devices over relatively short distance. It can be a networked office building, a school or a home, which are usually connected using LAN. These are usually owned by the same organization as attached devices. The data rates are much higher on LAN as compared to MAN or WAN. The topologies used in case of LAN include star, bus, ring, tree. The most heavily used is star and hierarchy. Next we move on to MAN. MAN is Metropolitan Area Network. It is larger than a LAN. A network which spans a physical area larger than a LAN but smaller than a WAN, such as a city, is called MAN. Example of MAN is WiMAX. A MAN is typically owned and operated by a single entity such as a government body or a large corporation. You can have a medium speed or data rate over MAN networks. Next, we have WAN, which is Wide Area Network. Wide Area Network spans a large physical distance. The internet is the largest WAN spanning the earth. Other example is if you want two branch offices of the same organization to be connected, usually a WAN technology is used for that. A WAN is a geographically dispersed collection of LANs which are connected to each other. Network device called a router connects LANs to create a WAN. Most WANs are not owned by any one organization but rather exist under a collective or distributed ownership or management. Data rates over WAN are comparatively low as compared to LAN as well as MAN. The topology used for WAN is usually a tree or a graph. Next we move on to different network topologies. A network topology defines how the nodes in the network are connected to each other. We can have a mesh topology, which is the simplest one, wherein each and every device is connected with every other device present on the network. We can have either a full mesh or a partial mesh based upon the connection. If each and every device is connected to every other device on the network, then it is called as a full mesh. In case of a full mesh topology, if you have n nodes, you are going to have n into n minus 1 upon 2 connections. In case of a partial mesh, we are going to have most of the devices being connected to each other, but few of the devices will not be having direct connections between the nodes. So such type of a topology is going to be called as a partial mesh. In this figure that you can see, this is an example of a partial mesh topology. Next, we move on to bus topology. Here you can see how the bus topology looks like. In case of a bus topology, you would be having multiple devices which are connected over a common media. In this type of a connection, the common cable over which multiple devices are connected will need to have terminators present at both the ends. If you do not have terminators present, then in that case there would be reflection of signal which cause noise or interference. In case of a bus topology, the common media or the common cable which is present is a single point of failure. That is, if there is some issue on the cable, none of the device will be able to communicate with any other device. Bus topology is usually used for smaller networks. Let us move on to the ring topology. Ring topology has got a reliability better as compared to the bus topology, since in case of a ring topology, each and every device has got two paths over which it can send the data to the destination. Each device present in the ring topology needs to receive the signal as well as should be able to transmit the received signal if it is not destined to itself. An example of a ring topology is a token ring or an FDDI type of a network. Next, let us move on to star topology. You can take a look at the star topology here. In case of star topology, there is a central device which would probably be an hub or a switch to which the other devices would be connected to. Whenever one device wants to communicate with other end device, the communication is going to take place via the central device. And hence, in case of a star topology, the central hub or a switch is a single point of failure. Next, let us move on to the tree topology. You can take a look at the tree topology as shown here. The tree topology is a combination of a star and a bus, and hence it is also called as a hybrid topology. The tree topology is the most widely used topology in case of large networks. Now let us move on to best effort networks. The internet is called as a best effort network because there are a lot of network impairments on any network, and the only thing that can be done is to make the best effort to reduce the impairments. We cannot get rid of the network impairments totally, but we do make a best effort to reduce the impairments, and hence internet is called as the best effort network. Consider an example where we have got a source and a destination which are located far apart and they are connected via some in-between nodes. Now, since source and the destination are located far apart, any signal that is sent by the source to the destination will not reach the destination instantaneously. There is going to be some amount of delay in receiving the sent signal by the destination, and hence delay is the first network impairment. Also, we have already seen that when we speak about packet switching, there are going to be multiple paths that are going to be used for transmission of packets. Some of the packets will go via one path and some packets via some other path. So in such type of a scenario, there is a possibility that one of the path, due to some issue, has a node which has failed, because of which there was some loss of information that happened. And hence loss of information is other network impairment. Now, in order to detect such type of loss, usually at the destination, whenever the packets are received, the destination is going to send an acknowledgement to the source. There is a possibility that the destination has received the packets and has transmitted the acknowledgement, but due to some issue on the network, the acknowledgement packet failed to reach the source. In such cases, the source will assume that the destination did not receive the packets, and hence the source is going to retransmit the packets to the destination. In this type of a scenario, the destination is going to receive duplicated packets. Hence, duplication is another network impairment that is going to take place over the network. Also, when we say in case of packet switching, the packets are going to traverse via different paths to the destination, there is a possibility that one path is a slower path as compared to other path. In such cases, if my packet 1 and packet 3 are transmitted over a fast path, but my packet 2 was transmitted over a slower path to the destination, The packet 2 will reach after packets 1 and 3. This is going to cause reordering of the packets. And hence these are the network impairments that would be caused on a network. Best effort is to be made to remove or to get or reduce the network impairments. Various approaches are used to reduce the network impairments, like layering and protocols. As a part of layering, OSI as well as TCP/IP are the two layer models that have come up. Each and every layer has got some protocol been defined. Protocols are a set of rules that are defined at each and every layer so that each device would follow same protocol and the two devices would be able to communicate with each other irrespective of the vendor. You can take a look at the OSI model and the TCP model in the image shown here. The TCP model is the actual implementation model, whereas the OSI model is just a reference model. Also, the TCP/IP model has come before the OSI model in timelines. The TCP/IP model is a 5-layer model, whereas the OSI model is a 7-layer model. The 7 layers of OSI model include physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and the application layer. Application layer is the topmost layer since it is closest to the applications which are used by the user, whereas the physical layer is the bottommost layer as the physical layer is closest to the transmission media. The TCP/IP model is a 5-layer model wherein the top 3 layers of the OSI model are combined into a single application layer. In case of a 4-layer TCP/IP model, the bottom 2 layers, that is the physical layer and the data link layer, would also be combined together to form a link layer. Let us move on to the OSI model. OSI model breaks up the functions or tasks of networking into smaller chunks called layers and defines standard interfaces between these layers. The layers break a large complex set of concepts and protocols into smaller pieces, making it easier to implement with hardware and software. Few of the benefits of OSI layer include less complex, easier to learn, easier to develop, multi-vendor interoperability, and modular engineering. Let us move on to protocols defined at each layer. At the data link layer, we have got Ethernet, Wi-Fi, and MAC protocols. Ethernet is IEEE 802.3. Wi-Fi is IEEE 802.11 standard. The network layer is divided into 3 parts. We have got the top, middle, and the bottom part of a network layer. At the topmost part of the network layer, we have got protocols like ICMP and IGMP. ICMP is Internet Control Message Protocol. It is used for testing the network. For example, when you use a ping to check whether a destination is reachable or not, ICMP echo request and echo reply messages are used. In case of IGMP, which is Internet Group Message Protocol, this is used for multicasting. Then we have got IP, which is present at the middle part of the network layer. IP is Internet Protocol. IP is used to create packets. When you want to transmit packets from source to destination, IP is going to append an IP header to create a packet. The IP header is going to have the source as well as the destination IP addresses present in it. At the bottom part of the network layer, we have got ARP and RARP. ARP is Address Resolution Protocol. This protocol is used to resolve an IP address to a corresponding MAC address. Once the resolution is done, ARP is going to populate this information in the ARP cache which is present on your device. Then we have RARP protocol, which is Reverse Address Resolution Protocol. This protocol is used to resolve your MAC addresses to IP address. Next, we move on to transport layer. At the transport layer, we have got two main protocols, the TCP, which is Transmission Control Protocol, and UDP, which is User Datagram Protocol. These protocols are used to define how the transmission from source to destination is going to take place. TCP is more reliable as compared to UDP, as TCP is connection-oriented protocol, whereas UDP is a connection-less protocol. TCP establishes a logical connection from source to destination before transmitting packet. In case of UDP, there is no such connection being established. Whenever a packet is to be transmitted, it is directly transmitted to the destination. TCP also makes use of acknowledgement in order to provide reliability to transmissions. Since there is no connection being established in case of UDP, there are no acknowledgements present as well. Next, at the application layer of the TCP/IP model, we have got protocols like FTP, which is File Transfer Protocol, which is used to transfer files between devices. Then we have HTTP protocol, which is used, for example, when you want to browse any site on your web browser. We have SNMP protocol, which is Simple Network Management Protocol. This is used for managing the network devices from a central device. We have SMTP, which is Simple Mail Transfer Protocol. This protocol is used in mail servers. And we have got DNS, which is Domain Name Server. This protocol is used to resolve domain names to IP addresses. We would be looking into details of this protocol in later slide. Apart from these, we also have got few other protocols present. At each and every layer of the TCP/IP model, you are going to have protocol data units which are created. That is, whenever a message is to be transmitted by an application onto the network, this message is going to go through the different layers of the TCP/IP stack, and each layer is going to create a PDU or a protocol data unit. At the application layer, the protocol data unit is called data. At the transport layer, we have got segment. At the network layer, we have packet. At the data link layer, frame is created. And at the physical layer, the protocol data unit is called bits. Next, we move on to OSI encapsulation. That is, we are going to take a look at whenever data to be transmitted from the source is going to be sent over the network, and it goes via the OSI or the TCP IP model. How does encapsulation take place in order to create protocol data units at each and every layer? So when you have got a message or data present at some application present on your source, this data is going to go to the application layer, and the application layer, the data would be called data. It then moves on to the transport layer, where the data is going to be broken down into smaller parts called segments. Each and every segment would be appended by a transport layer header. It can be either TCP header or UDP header depending upon the protocol that is being used. The header is going to have some information present which would be understood by the transport layer, and the same would be required by the destination transport layer. Each and every segment will then move on to the network layer. The network layer will append an IP header to create a packet. The IP header will have the source IP and the destination IP present. Then the packet moves on to the data link layer, where it is appended by a data link layer header, which consists of the source MAC ID and the next hop device's MAC address. And it consists of the trailer, which has got FCS or checksum, which is used in order to check if there are any errors present in the frame. FCS is going to be used at the destination when the destination receives the frame for checking if the frame has got any errors. Next, the frame moves on to the physical layer, where we have the protocol data unit called as bits. The physical layer converts the bits into signals which are understood by the transmission media used. For example, if air is the transmission media used, then in that case the physical layer will convert the bits to electromagnetic signals. If copper cable is the transmission media that is being used, then the physical layer will convert the bits into electrical signals, and so on. Once the bits are transmitted over the transmission media, any device which is present over the transmission media will receive the signals. Let us consider that we have got the destination that has received the bits at the physical layer. The physical layer will send the bits to the data link layer. The data link layer recognizes the frame structure, and it will recognize the data link layer header and data link layer trailer which is present. The data link layer trailer is used in order to check if there are any errors in the frame. If there are no errors present, then the data link layer header will be checked to check the destination MAC address. If the destination MAC address matches the address of this destination device, then the destination device will know that this frame is to be kept for itself, and it will strip off the header and trailer of the frame, and it will remove the packet which is encapsulated and send that packet to the network layer. The network layer is going to detect the packet and will recognize the IP header present in the packet. The network layer reads the IP header and it checks for the destination IP present in the header. If the destination IP address matches the IP address of the destination device, then the device understands that this packet is destined for it. Then the network layer removes the IP header present and sends the encapsulated segment to the transport layer. The transport layer will recognize the transport layer header, and it is going to check what is the port number which is present in the header. Based upon the port number, the transport layer will send the encapsulated data after reassembling it to a particular application which uses that port number. Like for instance, HTTP uses port number 80. So if port number 80 is the destination port present in the transport layer header, then the data is going to be sent to the web browser. Next, we move on to the different functions at each and every layer of the OSI model. The physical layer converts bits to signals compatible with the transmission media. Data link layer performs functions like flow control and error control. For error control, it uses forward error correction mechanisms. It also performs the function of framing, that is creating a frame, and physical addressing, which is MAC address. Network layer performs the function of logical addressing, which is IP addresses, routing, that is finding the best path from source to the destination in order to send the packets over that path. Transport layer focuses on issues related to end-to-end delivery of data. Error recovery, flow control, and fragmentation and reassembly. Session layer is responsible to start, control, and end the sessions. The presentation layer defines and negotiates data formats such as ASCII text, EBCDIC text, binary, JPEG, and so on. Encryption is also defined at the presentation layer. Application layer provides an interface between the communication software and any applications that need to communicate outside the computer on which the application resides. Next, we move on to details of each and every layer. We begin with the physical layer. The physical layer interacts with the transmission media that connects the network components together. It converts the frames from the data link layer into signals for transmission. It defines the procedures and functions that the application devices and interfaces should perform for the purpose of transmission. Data link layer is functionally divided into two layers. We have a logical link control layer and a media access control sublayer. The logical link control sublayer is responsible for flow control and error control, and the media access control is responsible for multiple access resolution. Let us take a look at what does multiple access resolution mean. So consider that we have got multiple devices which are connected to a common link. In this type of a scenario, if we have got more than one device that is trying to transmit some data to some other device present in this type of a network, then in that case, there is going to be a collision, since the transmission will happen on this common link which is present. And if there is collision, the data will be garbled and will not be understood by any device receiving it. This is called as multiple access type of a network. So a multiple access type of a network is a network on which multiple devices share a common media for transmission. There have to be some method in order to resolve this. So we have got certain set of protocols called multiple access protocols which have come up in order to avoid multiple devices trying to transmit at the same time over the shared media. The multiple access protocols are divided into three categories. We have random access, controlled access, and channelization. The random access type of multiple access protocol includes Aloha, slotted Aloha, reservation, CSMA-CA, and CSMA-CD. CSMA-CA and CSMA-CD are the most widely used protocols. Internet uses CSMA-CA. CSMA is carrier sense multiple access. In case of CSMA protocols, the carrier is going to be sensed before sending the message over the link. In case of CSMA-CA, which is carrier sense multiple access collision avoidance, the carrier is used to sense if there is some ongoing transmission on the shared media. If there is some ongoing transmission on the shared media, the device is going to back off the transmission using the back-off algorithm. In case of CSMA-CD, a small message or carrier is sent over the shared media in order to check whether there is some ongoing transmission. If there is some ongoing transmission that is detected over the shared media, then the device is going to send a jamming signal to rest of the devices present on the shared media, so that if any device wants to send data over this shared media, once they receive the jamming signal, they will use the back-off algorithm, and once the back-off timer is dead, after that only they will send the transmission over this link. Then we have got controlled access, in which we have token ring, token passing, polling, and reservation. In case of token passing, each and every device is going to pass a token to every other device. Only the device is allowed to transmit data over the shared media only when it gets this token. In case of polling, there is going to be one controller that is elected. The controller is going to poll the devices for data. Only when the controller has polled a particular device can the device transmit any data. Then we have reservation. In case of reservation, slots are going to be reserved for each and every device for transmission. The device can transmit data only in its reserved slot. And then we have for channelization techniques like FDMA, TDMA, and CDMA. FDMA is frequency division multiple access, TDMA is time division multiple access, and CDMA is code division multiple access. Next, we move on to the network layer. Network layer is responsible for delivery of individual packets to source and destination host. The network layer address or logical address identifies the source and destination when packets are routed across the network. The network layer provides routing mechanism. That is, network layer is going to define the best path from the source to the destination over which packets can flow. Network layer fragments the message if the message size is greater than MTU, which is maximum transmission unit. The IP header consists of certain fields which are used for this fragmentation and reassembly at the network layer. For IP addressing, currently IPv4 is in use, which is 32-bit addresses, but soon we are moving on to IPv6. IPv6 is 128-bit addresses, and hence we get more number of IP addresses as compared to IPv4. So in case of IPv6, we have 2 raised to 128 number of addresses possible. Next we move on to transport layer. Transport layer is responsible for process-to-process delivery of message between the two hosts. We say that transport layer is responsible for process-to-process delivery because transport layer is going to send the data that is received at the destination to the final application, and this is going to be done using port numbers. So the different application layer protocols have got different port numbers which are assigned. Based upon the port number present in the transport layer header, the transport layer is going to send that segment or the data to the application corresponding to the port number. Transport layer is also responsible for segmentation and reassembly. That is, on the sender side, the transport layer breaks up the application message into smaller parts called segments, and on the receiving side, it then reassembles the segments back to message before passing it to the application layer. The transport layer is also responsible for flow control and error control. Some of the flow control, error control mechanisms used include sliding window flow control, ARQ, which is automatic request for error control, in which it uses sliding window, or go back N ARQ. Next we move on to application layer. The application layer is the topmost layer of the OSI model. It provides services directly to the user applications. It provides user interfaces and support for services such as email, remote file access and transfer, shared database management, and other types of distributed information services. Few of the application layer protocols include DNS, DHCP, SNMP, SNMP, so on. We will take a look at DNS. DNS is Domain Name Server. Domain Name Server is used to resolve the domain names to IP addresses. If you have to remember IP addresses of each and every server with which you want to communicate with, it would be very difficult to work. But it is very easy to remember English names because you are habituated to it. But TCP/IP cannot work with English-like addresses. TCP/IP is designed to work with IP addresses, and hence you need to resolve the domain names which are easily understood by humans to IP addresses which is understood by TCP/IP. Domain name server is used to resolve the English-like domain names to IP addresses. The DNS domain namespace is based on the concept of a tree of named domains. Each level of the tree can represent either a branch or a leaf of the tree. You can take a look at the image here. The topmost domain is the root domain, which is dot. This is further divided into top level domains, for instance com, edu,
.org, and so on. These are further divided into authoritative domains like Google, Yahoo, etc. We will take a look at how DNS works. Whenever a user searches for a URL, he will type this URL in his web browser. For example, easy.example.com. The web browser will check for the resolution with the recursive DNS resolver. The recursive DNS resolver in turn will check if it itself has got the resolution for the domain name mentioned. If not, the recursive DNS resolver contacts the root DNS. The root DNS will provide the name for the top level domain. In the case here, it will provide the address for .com server. The recursive resolver then will contact the .com top level domain name server and ask for resolution to easy.example.com. If this server has got the resolution, it will provide the resolution. If not, it will provide the address of the name server of the authoritative DNS, which is example.com. The recursive resolver will then contact the authoritative DNS server for example.com and ask for resolution to easy.example.com. The resolution would be present with this server, and this server will provide the IP address to the recursive DNS resolver. The recursive DNS resolver will then provide this IP address back to the web browser of the user. Next, let us move on to DHCP. DHCP is Dynamic Host Control Protocol or Dynamic Host Configuration Protocol. It is used to configure devices that are connected to a network so that they can communicate on that network using the Internet Protocol. DHCP is used to provide configuration for IP address, the gateway address, DNS name server address. Whenever a client which is configured to use DHCP joins in a network, the client is going to send a DHCP discover message as a broadcast on the network. There can be one or more DHCP servers present on that network. All of the DHCP servers which are present on the same network are going to reply to the DHCP offer message, DHCP discover message with a DHCP offer. The DHCP server is going to provide an IP address from its pool of addresses in the offer that it has provided to the client. The client receives multiple offers from multiple DHCP servers, and the client will select one of the offer. The client will reply back to that particular DHCP server with a DHCP request message requesting for offering the DHCP configuration on lease. The DHCP server which receives the DHCP request will remove the address requested by the client from its pool of addresses which are available, and then it is going to acknowledge the client with DHCP acknowledgement message. The DHCP server provides the DHCP configurations to the DHCP client for a leased period of time. Once the lease expires, DHCP client will again have to request for a new configuration. Usually the client requests for a new configuration when 80% of the period of lease is expired. The process used by DHCP is called as DORA. It stands for Discover, Offer, Request and Acknowledge. Next, let us move on to SNMP. SNMP is Simple Network Management Protocol. It is an application layer protocol for exchanging management information between network devices. SNMP is used in cases where you want to manage multiple network devices from a central management device. This central management device is called as the SNMP manager. On this device, you would be running an SNMP manager software. The rest of the devices or networks which you want to monitor would have an SNMP agent software running on them. The SNMP agent software would collect the various metrics on this device, like the network throughput, or if the hardware is functioning correctly, like the fan speed or the heating of the device and so on. So there are going to be different parameters which are going to be checked by SNMP agent software, and this agent will keep the metric values in MIB database, which is Management Information Base database. An SNMP manager can request for any metric from SNMP agent software at any time. If the SNMP manager requests for a particular metric from the agent will check the metric present in the MIB database and will send that metric as a reply to the SNMP manager. These are called as SNMP response messages. Agent software can also give SNMP trap messages to the SNMP manager. The SNMP traps are going to be triggered if there is some issue in the device. Like for example, the CPU utilization crossed 80%, or the fan is not operational due to some reason. So these type of events might trigger SNMP traps which are sent to the SNMP manager. The SNMP manager will alert based upon the trap received. Next, let us move on to network devices. At the physical layer, we have got devices like repeaters and hub. Repeater is a simple device which is going to amplify the signal which is received and send it on the devices connected. Hub performs the function same as that of the repeater, just that it has got more number of ports. Hence, hub is sometimes called as a multi-port repeater. Whenever a hub receives some message or some signal on one of its ports, the hub will filter and amplify that signal and send it out on the rest of the ports. Next, we have set of devices which operate at data link layer like bridge and switch. Bridge is a software implementation, whereas switch has got implementation on ASIC. Switch has got more number of ports as compared to bridge, and hence switch is sometimes called as a multi-port bridge. The image shown here is an image of a switch of the series 2950. Switch is also having multiple ports, as you can see in the image. But switch can also perform filtering because it has got some interlesions since it is a data link layer device. So switch can perform filtering of the messages based upon MAC addresses. That is, if a switch receives some message on one of its ports, the switch can read the data link layer header to find out what MAC address is this message destined to, and accordingly send the message out of the port on which the device with that destination MAC address is connected. Next is the network layer device, which is router. You can see in this image how the router looks like. Router has got less number of ports as compared to switch or hub. So here you can see the router has got only 2 fast Ethernet ports. It also has got some additional slots in which you can put some additional interface cards. Like for example, if you want to connect WAN links to a serial interface, then you can use the serial interface cards like WIC1T or WIC2T in the slots. Since router is a network layer device, it can understand IP addresses and it can perform routing using IP addresses. Router is the most intelligent device, followed by switch and then hub and repeater. Next, let us move on to collision domain and broadcast domain. A collision domain is a section of a network where data packets can collide with one another when being sent on a shared medium. And a broadcast domain is a logical division of computer networks in which all nodes can reach each other by broadcast. To understand collision and broadcast domain, let us take one example. Here you can see a router which is connected to 2 switches. The switch are in turn connected to end devices or hub. Router, being a layer 3 device, can understand IP addresses, and hence router can divide the entire domain into broadcast domains. Because one side of the router's interface would belong to one separate network, whereas other side of the router's interface will belong to a separate network. Hence, you can have broadcast restricted within this domain. So, the domain inside which you can restrict the broadcast to, that domain would be called as the broadcast domain. So here you can see these 2 blue circles. These are the 2 broadcast domains being created. In order to calculate the number of collision domains, we would take a look at the number of connections to the switch. As switch can perform filtering, each and every interface of the switch will form a separate collision domain. Hub cannot perform filtering, and hence hub cannot divide the domain into multiple collision domains. So if I have got 2 devices present on this hub, if both of these devices make transmission simultaneously, then there is going to be collision. But in case of a switch, if I have got 2 devices which are directly connected to my switch, and if these 2 devices make some transmission simultaneously, the switch is capable of filtering, and hence it will not allow the signals to collide. So in order to calculate the collision domains, let us find out the number of interfaces of the switch having connections. So this is first one, this is the second interface, this one is the third. The router also divides domain into collision domains. Okay, but this is considered to be a single network, and hence we will count it as a single collision domain. On this side also we have this as a separate collision domain, and these two different interfaces of the switch as two separate collision domains, and hence the number of orange circles that you can see here, which is 6 collision domains.
That is all for this session. Thanks for watching. Please leave your comments. It would help me to create better videos for you.